Let's discuss the filling of the electrons in transition elements, because in transition elements from d block elements where we got so many exceptions in filling the electrons. So for you can see here from scandium, you know that atomic number 21. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d1. So this is the filling of the electrons in respect to orbitals. You may get one doubt, because everything is in the sequence order, right? So 1, 2, 2, 3, 3. In between 4 and next 3 is coming. Why this happens? Why the sequence is not in a regular pattern in mask? So this is because of this. One Afubo principle says that filling the electrons in the lowest energy levels. Okay. But even though it has a principal quantum number 4, it is greater than this 3, but it is the lowest energy. How? So let's explain by the n plus L rule. This says that n plus L rule. Actually, what it tells that n is nothing but the principal quantum number, that is principal quantum number, and L is nothing but the subshells. Subshells are nothing but S, P, D, like this. S, P, D, like this subshells. So they have the respective values will be there. S is a 0 value, P 1, D 2 will be there. So just you substitute. Okay. First you see this one 4s orbital, right? So 4, principal quantum number is 4. I am going to substitute n is equal to 4 plus L. L means 4s orbital is S orbital value is 0. So what happens? Now we are going to get 4. Okay. Next come to the 3D. So here principal quantum number is 3. That is n is equal to 3. Plus what will be the value of D? D is equal to 2. When you substitute 3 plus 2 as you are going to get a 5. So that's why 4s is the lowest energy level, and whereas 3d is the highest energy level. So that's where Apophos he says that, so always fill the electrons from the lowest orbital. So that is 4s is the lowest orbital and 3d is the highest orbital. But in case of transition elements, what happens there? So simply instead of writing this, I am going to write this as an argon, because you know that argon is an 18 electron, and this is also stable element also. So 1s2, 2s2, 2p6, 3s2, 3p6. So up to here I am writing as a argon, and remaining I am going to write as this. That is 3d1, 3d1, 4s2. Why I have interchanged here? So even though here Apophos principle, here exception case will be there in transition elements, because what happens? So this is we consider as the lowest orbital energy. This is the highest one. But what happens here in the d block elements? These they are going to consider as the outermost orbit, outermost electrons. Okay. So as compared to the radius, not we are not considering here the energy levels. Only we are considering the radius. So in the d block elements, we are going to consider as this is the outermost orbital. So like this, you can feel here. This is scandium. Next, you can see the titanium. Titanium is atomic number is 22. Same as it is argon. So, okay, 3D. Next, one electron will be, I am going to add here 4s2, like this, 22 now. Next, scandium, titanium, vanadium, 23. So, same as it is argon, I am going to write here. And just I am going to add one more electron, 3d3, 4s2, like this. Scandium, titanium, vanadium. Next is chromium, atomic number is 24. So, argon. Now you can tell that 3d4, 4s2. Okay, so this is the absolutely this is wrong. Why? Because we can tell that in the filling the electrons, this chromium and copper is atomic number 29. Both have exception case. Why? Because D block, you know that maximum it contains the 10 electrons, and I am going to write 5 electrons. Okay, this is 5 electrons, because D5 always D5 and D10 always they are stable, because he says that completely half filled orbitals and fully filled orbitals are always stable. So what happens in case of chromium, when I write the 3d4, so that is for 3d4 here now, 3d4, and here 4s2 will be there. So what happens? In order to get stability of this chromium atom, what happens? It requires one electron from the outermost shell orbitals. So that's why in d block elements we are going to place the 4s orbital as the outside. They are considered the valence electron, because metals are highly electropositive. Sometimes it ready to give the electron electrons. Okay, these are the outermost electrons. So what happens, in order to get the stability, so it is going to acquire one electron to become stable. Now chromium is become stable. So now I am going to write as 4s1 and 3d5 like this. 3d5. But as it is, manganese will be as it is will be there. Argon, because atomic number is 25. Argon here 18. 18 plus 2, 20, 20 plus 5, 25. So like this will be there. This is the manganese. Next, continue the elements. The iron, this is the 26 atomic number. So argon, 18 plus 2, 20, 20 plus 26. Argon next, cobalt will be there. Cobalt atomic number will be 27. So similarly, I am going to write as argon 3d7 4s2 like this. Cobalt next, nickel 28. So here argon 3d8 4s2. But whereas in copper we are going to find the exception case. So argon, and instead of writing 3d9 I am going to write 3d10 4s1. Once again, this is a stability parameter. Okay, what happens here in the general case of the copper, we are going to write 3d9 4s2, right? So what happens? How the electrons will be there? In order to get the stable, so copper, in order to get the stable, it requires only one electron. It requires only one electron because one electron is less in this orbital. So what happens? Here the 4s2, which is going to give the one electrons to this copper to become this stable. So that's why we are going to write the electronic configuration as 3d10 4s1, but not 3d9 4s2. And zinc I am going to write as it is. That is argon 3d10 4s2. So like this, we can fill the electrons in the respective orbitals in the transition element. So we should concentrate on the filling the electrons in chromium as well as copper, because these two have the exception cases. So instead of writing 3d4 4s2 in the chromium, we should write as a 3d5 4s1 because of the stability parameter. And in case of copper, instead of writing 3d9 4s2, we should write 3d10 4s1 because of the half filled orbitals and completely filled orbitals are always stable. If that copper and chromium it is not stable, means it requires the one electron from the outermost orbital, that is called 4s2. It requires one electrons to become stable.